Alright, so what we're going to do is we're going to go over how to calculate a precipitate problem in with a KSP situation. So first thing you have to notice is that there's 4 steps to it. The first thing is using solubility rules, which we learned in chapter 4, to determine which one's going to be insoluble, because remember KSP focuses around compounds that are considered slightly soluble, but using solubility rules are insoluble. Second step is you're going to write out the reaction like we did before and a KSP expression. Third step is you have to calculate the new molarity, because anytime you're doing a precipitate problem, what you're going to do is you're going to mix 2 solutions, which is going to create a new volume, similar to what we had to deal with when we were doing titrations. The last step is you're going to plug the new molarity values into the KSP expression and calculate the Q. Remember, a Q calculation from chapter 14 is the same thing as a K calculation, except just you're comparing the values to see where they're relating to K. That's the whole point of it. So you're basically calculating Q, so then you can compare it to the KSP to see whether or not a precipitate will form. So those are the 4 steps. So start with our problem. Solution is prepared. If you notice a couple things, you're mixing a solution of 750 milliliters of one solution, 300 milliliters of the other. One solution contains CeNO3, the other solution is KiO3. And then using the solubility rules, you'll notice that CiO3, and they give you the fact that they give you the KSP, tells you what the precipitate could possibly be if there's enough in there to cause a precipitate. So that's what a problem looks like. You're given two volumes, 2 molarities, and then they're going to ask you in the problem, does a precipitate form? That's the whole point of the problem. So step 1, you basically use solubility rules to figure which one's going to be insoluble or slightly soluble. We know KNO3 is always soluble, so we don't have to worry about that. So that's going to be our precipitate, or our slightly soluble compound, similar to what we've already done in chapter 16. You're going to write the solid on the left-hand side. So CE parentheses IO3, 3. On the left, it's going to break into CE3 plus and 3IO3, 1 minus. If I go to write that into a KSP expression, remember it's going to be nothing on the bottom because we simply don't count solids in an equilibrium expression. So you're going to basically put the CE, coefficient's 1, so it's going to be the exponent's going to be 1. IO3 drops in there, coefficient's 3, so there it gets the exponent 3, and that's equal to KSP. That's very similar to what we've already been doing in this chapter. It's the same thing. You're just using solubility rules because they're not telling you what the compound is, but as a student in AP, you should be able to figure that out. Next one. Calculate the new molarity for each ion. Be sure to divide by the new volume. If you remember, molarity times liters will always get you moles. We did that in the previous chapter. You need to know that whenever you're dealing with solutions in chemistry, you just take molarity times liters and it will always give you moles. So when you're calculating molarity, the idea behind molarity is just moles over liters. So the first thing is find the molarity, or excuse me, find the moles, then put it under the liters underneath, and you will find the molarity of each ion. So if you look, coming back to the problem, the first one, 750 milliliters of 4.0 times 10 negative third CnO3. We don't really care about the NO3 because it's soluble, but we need to find the concentration of the Ce3 plus ion. So what do? We take the 750 milliliters, I change it to liters, multiply times the molarity, which is 4.0 times 10 to the negative third. I get 0.003 moles of Ce. So I have my moles on top. I just took molarity times liters and I got that. New volume. Well, the new volume comes from the fact that you're mixing 300 milliliters and 750. So I'm mixing 300 milliliters plus 750 milliliters. That's going to be my new volume. So my new volume is going to be 1050 milliliters, or 1.050 liters. So I come back over here. You see that in the calculation. You see that right here on the bottom. I put the new volume on the bottom because molarity is going to change when you increase the volume. So I take the moles that I found, 0.003, divided by the new volume. I get my molarity. Stuff we've been doing for quite a few chapters, should be no big deal. What about the iodate ion? Well, I come back over here. If you look, pick a different color. They told me I have 300 milliliters of 0.20 times 2.0 times 10 to the negative second KiO3. We don't care about the KiO3. The K is insignificant because it is completely soluble. So really we just focus on the IO3. Again, it's going to still be the same new volume because you're combining 300 and 750. So I come back over here and I take the liters, which is going to be 0.300 liters since it's 300 milliliters, times 2.0 times 10 to the negative second. Again, molarity times liters will always get you moles. So that's how many moles. I have 0.006 moles of IO3 minus. The last step I have to do is divide by the new volume. It's the same solution, so it's going to have the same new volume. I drop that on the bottom, and I get my concentration of IO3 minus. So now I have my two ion concentrations. Well, if you remember, previous to this, we wrote a Ksp expression. Ksp expression is the same thing as the Q expression. So what do? Well, I come over here, I take my Ksp expression, I'm going to take the values. If I go back up here, my value for Ce3 plus is 0.00286. So I'm going to drop that value right in there, 0.00286. My value for IO3 minus, if I look at it, is 0.00571. I come back to the expression. I drop 0.00571 there. I have to raise that to the exponent of third. I do the calculations. So I'm just taking the values, my new molarities for each of the ions. I throw them in the expression. I calculate a Q. I get 5.32 times 10 to the negative second. If you remember, in the original part of the problem, they gave me the Ksp, or they could, if they give you as a book problem, they'll have you look it up. If you look right here, basically what you end up with is you compare the two values. So I have my value for Q is 5.32 times 10 to the negative second. My Ksp value is 1.9 times 10 to the negative 10th. It's the same kind of process that we did in chapter 14. You're comparing Q to K. In this case, my Q at 5.32 times 10 to the negative 10th is larger than 1.9. That means, what do we write chemistry style? We would write Q is greater than K. So that means the reaction, well, remember when K is ever greater, it always goes backwards. When you go backwards, notice precipitate is when you form a solid and a liquid. So if the reaction is, if Q is passed, we're past C world, if you think about it like that. It's going to drive the reaction back this way. Notice there's a solid there. So as you go this way, you're going to always form a precipitate. So you're going to form precipitate. So you say, yes, a precipitate will form. And that's all you have to do in one of those calculation problems. If Q is less than K, no precipitate will form. If they're equal, like when we did the at C world for equilibrium, that means we say it's a saturated solution. So that's the definition of a saturated solution. So 4 steps to doing a precipitate problem. Use your solubility rules. You should know those. If you don't remember them, look them up, go through them. We're going to start using them a little bit more to write reactions. Figure out who's insoluble. Write out the reaction. Write out the Ksp expression. Then you're going to calculate the molarity of each ion. That starts with molarity times liters is going to get you moles. Drop the new volume in liters on the bottom. It's supposed to be an L. Last but not least, go back to the expression, plug it in, and compare the values. If Q is greater, precipitate will form. If K is greater, no precipitate will form. All right, and that's all you have to be able to do to calculate a precipitate problem. It's not bad, actually. Not bad at all. All right, have a good rest of your weekend.